You clicked on this video because you have seen code that divides image pixels by 256 or by 255, and now your model trains slower than expected. The stakes are real because the difference between those two numbers determines whether high-contrast features vanish into numerical noise during training, starving your neural network of critical signal information right when it needs them most. By the end of this explanation, you will understand exactly why dividing by 256 creates a silent failure mode in modern deep learning pipelines, and how correcting this single line improves convergence speed significantly. Let us start with the fundamental question that confuses so many junior engineers. Why do we normalize image data at all? When you load an RGB image into PyTorch or TensorFlow, each pixel channel holds integer values ranging from 0 to 255. This 8-bit format is legacy hardware design meant for storage efficiency. However, neural networks operate in floating-point arithmetic where numbers like 1.5 or 3.4 are natural and expected. Feeding raw integers directly into a network forces the optimizer to work with massive gradients that can cause instability during weight updates. Normalization scales these values down so they fall within a standard range between 0 and 1. This creates a stable probability distribution for gradient descent to navigate without exploding or vanishing. Here is where the confusion begins in production codebases across GitHub repositories. Some developers divide their pixel tensors by 256, while others use 255, assuming both are mathematically equivalent because they look similar on paper. This assumption leads directly into a hidden trap that affects training convergence and model accuracy over time. The difference seems trivial until you examine the mathematical mapping of values to the normalized interval. When you divide by 256, the maximum value of 255 becomes approximately 0.984. More critically, in integer arithmetic systems common in embedded pipelines or older C++ code, dividing 255 by 256 results in a truncation that maps the brightest possible pixel to exactly 0 rather than 1. Quick resource note: I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. This creates what we call an off-by-one error in scaling logic. The Fast LED library documented this exact issue in their bug reports regarding color conversion functions where integer overflow and rollover errors occurred during RGB to HSV approximation. In those specific cases, a value of 218 scaled incorrectly due to the division by 256 resulted in data loss that corrupted the entire signal chain. While modern deep learning frameworks use floating-point math which avoids strict truncation, they still suffer from a different but related precision flaw. Dividing by 256 creates a systematic bias where the upper bound of your distribution is compressed more than necessary compared to dividing by 255. Consider what happens when you normalize an image using 256 instead of 255. The resulting tensor values now span from 0 up to approximately 0.984, leaving a gap at the very top of the 0-1 interval that would otherwise be filled if you divided by 255. This missing slice represents high-intensity signal information that corresponds to bright highlights and strong edges in your input data. When your model processes images with significant contrast or sharp transitions, these features fall into a region where the gradient flow is weaker than it should be because the values are artificially capped below their theoretical maximum of 1.0. This subtle compression degrades gradient descent performance over many training epochs. Research and community discussions on PyTorch image captioning confirm that standard practice dictates dividing by 255 to preserve the full dynamic range, yet few practitioners realize how this affects numerical stability in loss functions near the boundary. In color-sensitive architectures like HDR to SDR converters or pose estimation models using LiDAR data, this scaling mismatch manifests as a specific green overabundance or visible color shift, because the human eye and convolutional filters are more sensitive to quantization errors in the green channel where intensity variations occur most frequently. The error amplifies through backpropagation, causing the model to struggle to learn high-frequency details that drive accurate predictions. The convention of dividing by 256 is largely a legacy artifact from an era when processors optimized for power, of 2 arithmetic were dominant, and division operations needed to be as fast as possible using bit shifting techniques. While this optimization made sense on older hardware, modern GPUs utilize floating point units where the computational cost difference between dividing by 255 or 256 is negligible compared to the benefit of preserving full precision in your input distribution. Continuing to use 256 normalizes data into a non-ideal probability space that introduces numerical instability when calculating loss functions near the boundary, forcing the optimizer to work harder to recover lost information during early training stages. When you fail to correct this pre-processing decision in your data pipeline, you create a silent failure mode where the model trains on a compressed signal space for hundreds of epochs before it can even begin to compensate for the missing high-frequency detail. You might see loss curves that appear stable but converge slower than theoretical benchmarks suggest because the gradient magnitude is dampened by the scaling mismatch. In practical terms, this means your junior engineer colleagues could be training models that require significantly more computational resources and time just to reach a baseline accuracy that would have been achieved faster with correct normalization. The difference between 255 and 256 is not a minor rounding error. It is an architectural decision that dictates how much of the original signal reaches the learning algorithm intact. Adopting division by 255 aligns your data pipeline with modern floating point precision standards used in PyTorch and TensorFlow, ensuring that every pixel value from 0 to 255 maps correctly into the E0, 1 interval without creating a hole at the top of the distribution. This simple change restores full gradient flow for high contrast features, allowing your model to learn faster and achieve better local minima during training. It is a critical step in production-grade development that separates hobbyist experiments from robust machine learning systems capable of handling real-world visual data with fidelity. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.